Hello there, this is tutorial for week 6. So we are going to attempt one of the question that I gave from the homework. Okay, so this question is a uniform distributed load 66 kilonewton. Okay, it's support over 6 meters span, and this is how the structure look like. So determine the smallest allowable length L of beam CD if a W6075 beam is not to be overstressed, and then we have to find what is the most economical beam for CD, and we are going to neglect the weight of both beams. Okay, so this is a very classical, very interesting problem. So the first thing we do is we sketch our free body diagrams. Okay, so we sketch our FBD. Okay, then we're going to have our, so this is our X, and this is our Y, moment about Z. Okay, then we're going to sketch our free body diagram first. So we're going to sketch, now this is a two free body diagram. Okay, so we have two sections. So this is the top part. So over here we know that there's a load coming down. Okay, and this is equal to 66 times 10 to the power 3 L. Okay, and then we know that we have two reactions. So I'm also going to call this point C and point D, and over here we are given two reactions, and the reaction over here, because the structure is symmetry in terms of loading and geometry, C and D will take half the load each. Okay, so that's why it's 66 divided by 3. You have 33 times 10 to the power 3 L. And then we apply Newton's third law: action equal reaction, same in magnitude, different direction. Okay, so all these share the 33. So all these, okay, they share the 33. Okay, I'm going to put this here. Okay, they share the 33 times 10 to the power 3 L of point load. Then you have the structure, the lower part. Okay, so we have the lower part structure. And from here you have reaction forces AY, and then you have reaction forces over here BY, and to label our points, is our point A, point C, point D, and I think the last one is our point B. And then we have load coming down again. Okay, we have loads. So we have a load coming down this way, this direction, and this direction. And these loads are equal to 66 times 10 to the power 3. Okay, and then the length. Okay, so what is the length? Because even this distributed load. So like what I told you guys before, the length is really important. You get your length wrong, that's where problem will come. So we are aware straight from the center. Okay, we are aware that this distance from the center to the center, okay, we are aware that this is our length, and this is 3 meters at midpoint. Okay, so this is 3 meters. Okay, so I will call this point E, right? So I'll label point E later. So you know that the distance from here to here, we know that this distance from here to here, right, is equal to L over 2, small l over 2. Why that's the case? Because the top beam, this is L. Okay, so the 66 times 10 to the power 3 is equal to 3 meters minus by L over 2. Okay, and then the distance from here to here, this distance from here to here, okay, that I've just drawn, this is 1.5 minus by L over 4. So the most critical thing about this example is to sort out your distance first, okay? And then the top part, from here to here, this is L over 2. Okay, same thing. So now, when we analyze this structure, we know that failure will occur at point E. Okay, so this is where maximum will occur. Okay, so now once you sort out all this, look at the information that we are given. We know that stress allowable is equal to 140 times 10 to the power 6 Pascal. Okay, so with this information, we have to find the maximum moment. And the maximum moment for this case, we're going to use stress allowable, which is also equal to stress max, is equal to stress max. And this will be equal to M max divided by S mean. So from the table, okay, S mean is equal to, so if you look at the shaft or the beam, you have W 460 74. So W 460 74, W 460 74. So it's this one. Okay, 74. We know that is equal to 1460 times 10 to the power 3. Okay, so we know that this is 1460 times 10 to the power 3 millimeters cube, or 1460 times 10 to the power minus 6 meters cube. And this is because for W 460 times 74. Okay, this is because of our W. So from here, we can find our maximum moment or maximum moment at point E. So this will be equal to 140 times 10 to the power 6 multiplied by 1460 times 10 to the power minus 6. So the outcome from this is equal to, so 140 power 6 times 1460 power minus 6 is 204.4 times 10 to the power 3 Newton meter. Okay, so that's what it's found. Then from here, you're going to do static analysis. Okay, we're going to do static analysis. And we are going to do summation about forces in the y direction is equal to 0 for the lower beam. Okay, so I'm going to call this lower beam. And I'm going to call this upper beam. Okay, so we're going to call lower beam. So we're going to analyze static analysis for lower beam. So we're going to do summation of forces. Okay, so positive is going up. Oh, we already wrote that already. So this is equal to AY plus BY. So you have AY, okay, plus by BY, right? then you minus twice of the 33 times 10 to the power 3 L, okay, and then you do twice of the 66 times 10 to the power 3 bracket 3 minus L over 2. Okay, so I'll write it here. So 2 33 times 10 to the power 3 L, right? Then you have twice again of the 66 times 10 to the power 3, and then you have 3 minus by L over 2. Okay, so this is L, right? And then the whole thing is equal to 0. Then note, due to symmetric geometry and loading, right, AY is equal to BY, right? So when that's the case, you have 2AY, right, minus by 66 times 10 to the power 3 L. Okay, so you will have 66 times 3, so you have 396 times 2, so 2 times 66, 396, so minus 396 times 10 to the power 3, and then minus minus plus 66 times 10 to the power 3 L, the whole thing equal to 0. So from here you can cancel the L's, so you have AY is equal to BY, and this is equal to 198 times 10 to the power 3 Newton. Okay, so this is what you see now. Okay, so this is critical information. So likewise for this. Okay, so these two information are important. So from here, we're going to take moment. Okay, I'm going to split the page into two. We're going to take moment, okay, of the lower beam. So again, we're still focusing on the lower beam. Okay, we're still focusing on the lower beam. Okay, so you only need to consider half. Okay, you don't need to consider full beam. We're going to analyze the beam at E. Okay, because this is due to failure. So we have this. So you know that AY, right? So summation about moment, Z, and we're going to take the moment at point E. So this will be equal to AY, right? So AY, so minus equal to 0. So you have AY, so minus AY multiplied by 3. Okay, and then you have 66 times 10 to the power 3 minus L2. So this is going in clockwise, plus by 66 times 10 to the power 3. Okay, close bracket. Then multiply by 3 minus L over 2. So this is still the load, and then you have to multiply by 3 minus by 1.5 minus by L over 2. Okay, so 3 minus by 1.5, right, minus by L over 4. So this term over here, this is this distance. What is that distance that we are dealing with? So it's this distance that we're dealing with, Remember, we are taking moment at point E now. So we are taking moment here at point E. So this is where you have 3 minus by 1.5 minus by L over 4. Okay. And then you have plus by 33 times 10 to the power 3 L. Then you multiply by L over 2. Then you finish off with plus by ME. Okay, so finish off by having a ME plus by moment at point E is equal to 0. We know what is moment about point E because we found that already. So moment about point E, so this is our moment at point E. Okay, we found that. So next is just matter of substitution. Okay, so I think I have another close bracket down here. So this will be equal to minus 198 times 10 to the power 3 multiplied by 3, and then you have plus by 66 times 10 to the power 3. You sort what is inside, so 3 minus by L over 2 bracket, so you will have 1.5 plus by L over 4. Okay, then plus by 16.5 times 10 to the power 3 L squared. Okay, and then you plus by your moment at E, which is equal to 204.4. Okay, which is equal to 204.4 times 10 to the power 3. The whole thing is equal to 0. Then you have minus 594 times 10 to the power 3. Then plus by 66 times 10 to the power 3. You sort up the internal terms, so you get 4.5 minus by L squared over 8. Okay, and then you plus by 16.5 times 10 to the power 3, and then you plus by 204.4 times 10 to the power 3. The whole thing is equal to 0. Okay, then you have minus 389 0.6 times 10 to the power 3, and then you have plus, so 66 times 4.5 is 297 times 10 to the power 3, and then you minus 8.25 right times 10 to the power 3 L squared. Okay, then plus by 16.5 times 10 to the power 3. The whole thing will be equal to 0. Okay, so from here we come up with minus 92. Okay, so minus 92.6 times 10 to the power 3, then plus by 8.25 times 10 to the power 3 L squared equal to 0. Therefore L is equal to, the two possibility is equal to so L squared first is equal to 11.224. So L is 3.35 026 meters. Okay, so we're going to select, so we're going to choose, obviously it cannot be minus, positive 3.35026 meters. So this is your answer. Okay, so now you know your length, so you want to find suitable beam for CD, beam CD, and cos is the controlling factor. So IE, minimum cross-sectional area. Okay, then again the beam will fail at the center. Okay, so I'll see, can I squeeze? Okay, so the beam will fail at the center, so we're going to go midway. Okay, so we know the load, I'm going to draw it in red, the load over here is 33 times 10 to the power 3 L, and then we know, we are aware now, the distance from here to here, right, the distance from here to here is 3.3506. okay, 3.35026 divided by 2, and then we know that the load over here on the top, evenly distributed load, and this will be 66 times 10 to the power 3 multiplied by 3.35026 divided by 2. Okay, and then finally we know the distance from here to here, from the distributed load to here, so we know that this will be equal to 3.35026 divided by 2. Like what I said, always solve out your distance first. Okay, so we're going to take the I'm going to call this point F. Okay, so we're going to take summation of moment Z at point F is equal to 0, positive bending moment, positive shear, so this is our MF. Okay, so this will be equal to 33, so minus 33 times 10 to the power 3 multiplied by our distance L, 3.35026, multiplied by our perpendicular distance, 3.35026, the whole thing divided by 2. Okay, then it's plus, you have 66 times 10 to the power 3 multiplied by 3.35026 divided by 2 multiplied by 3.35026 divided by 4. Okay, sorry, this one is 4, I do apologize, I got it wrong. Okay, divided by 4, and then from here, then you have your plus by your M max, or M at point F, which is also equal to point max. So over here, your M at point F is equal to 92.6 times 10 to the power 3 Newton meter. So your S mean, right, will be equal to your moment 92.6 times 10 to the power 3 divided by the allowable load, which is 140 times 10 to the power 6. So therefore the S mean, okay, so 92.6 power 3 divided by 140 power 6 is equal to 661.4 times by 10 to the power minus 6 meter cube, or 661.4 times 10 to the power 3 millimeters cube. So 661.4. So if you go to the table 661.4, so you look at 661. So you're going to select, okay, not too big. Too big will be too expensive. We're going to select, okay, so we're going to select this one. Okay, so we're going to select, okay, we're going to select for upper beam, which is W360 by 44. Okay, I'll come back again and we'll do another example.